Yo, what's going on, YouTube? I believe that we should be live any second now. How's your day going? I hope you're having a beautiful day. Thank you for tuning in to my math video. Today we will be practicing linear algebra again. Today is day 30, whatever. I don't remember. We are working through this book by Fraleigh and Beauregard. It is my favorite book in linear algebra. It's what my introduction to linear class was taught out of. What I really like about this one is I think it's a very nice blend of theory and computation. So it's very computation forward. At least the first exercises of every chapter are fairly computational, but the sections are written like a real math book, like definition, theorem, proof. It does not skip the proofs. It's clearly written, in the style of an upper division math book. But it's still very accessible to anybody, to engineers, to people who just want to use linear algebra. Anyway, so we are in chapter 4 on determinants now. And I went ahead and wrote down the problems that we're going to work today. So we're going to be doing a problem solving stream. I will be explaining the concepts as we go. But we're going to be focused on exercises and focused on problems. Some of them are a little bit more conceptual. Like, notice that this one says, show that this vector is perpendicular to both B and C. So we don't have any numbers, we just have letters the whole way through. And that's a beautiful thing. Like, to me, real math is when you are showing concepts that apply to any arbitrary number, or at least mathematical facts that satisfy certain assumptions. So, we are calculating determinants today. We have a couple of calculation problems of actual determinants. This one's pretty scary looking. It's a 5 by 5 determinant, and oh my gosh, doing a 5 by 5 determinants, from the definition, like in section 2, is a pain in the butt. So we have to have something more clever. We're going to solve this one through just from the definition of a determinant, and maybe a special rule for 3 by 3 determinants. And then in this section, I'm going to mention a couple of the properties that we can prove through theorems to simplify our lives and, make it much faster. Then we have a fourth section on linear transformations and determinants. The book calls this an optional section. It's quite nice. I really like the section. I hadn't learned these concepts in my intro to linear class. So I think we'll get through those. And then possibly afterward, we could take some notes and just do like a chill study with me type of stream. So if you're interested in that, you could fast forward. If you want to see these problems, if you want to work the problems on your own and then compare to my solutions, I invite you, please pause the video and try to solve these on your own. You can pause the video at any time. Okay, so now with that out of the way, I'm going to assume that you have tried this problem. So what does it mean for a vector, for vectors u and v to be perpendicular, it says. So here's a symbol that looks like two right angles. U is perpendicular to v if and only if the cosine, if they're perpendicular, if two vectors are perpendicular, then the angle between them would be pi over 2 radians, right? If the angle, also known as 90 degrees, right? If the angle between two vectors is 90 degrees, well, then the cosine of that angle should equal 0, because that's the cosine of pi over 2. And we also have this formula that the cosine of let's see, how do I write this? We also know this formula from a previous section, that u dot v is equal to the length of u times the length of v times the cosine of the angle between them. So, therefore, u is perpendicular to v if and only if u dot v is equal to 0. So you could pause and think about why that is true. But, I mean, cosine theta is 0, so whatever the lengths are, u dot v should be 0, right? Okay, so now this problem boils down to show that P is perpendicular to B and P is perpendicular to C. In essence, P dot B is equal to 0 and P dot C is equal to 0. So when I say dot, I mean the dot product of these two vectors. Oh, I forgot to turn on some background music. Let's listen to some background music. This is my classical guitar recital from a recent classical guitar recital. Where did it go? Where did here it is. All right, so let's listen to my classical guitar recital. I hope you all enjoy it. Let me know if the volume should go up or down, and if anybody's watching the VOD, please say hi and let me know if you enjoy this. Okay, so now we've simplified the problem to showing this. Now, recall A dot B plus C equals A dot B plus A dot C. Is this true? I think it's true. Yeah, that should be true. That should definitely be true. P dot B is equal to everything that's in equation 3, the determinant B2, B3, C2, C3, I minus determinant B1, B3, C1, C3, J, plus determinant of B1, B2, C1, C2, K, oops, I used a square bracket, dot product with B. Okay, and this property works both ways. So A dot B plus C is A dot B plus C plus A dot C, and A plus B dot C is equal to A dot C plus B dot C. So the dot product has this linearity of addition. So now we have B2, B3, C2, C3 times the vector I dot product with B. So I'm distributing through the dot product. I don't know if this is the best solution for this, but this is my first intuition, and there may be a better solution. I don't know. I think that this is going to work. I like this approach. because I see why it's going to be nice. K dot B. Okay, so I'm running out of space there. Let's just scooch everything over just a little bit. Hey, try to do that on a chalkboard, y'all. Try to do that on a chalkboard. Okay, cool. Now, let's also say, recall, a scalar multiple, let's see. Yeah. A scalar multiple times a vector dot product with another vector. Let me really clarify that the A and B are vectors and K is a scalar number. It's just a regular old scalar number. This will equal the constant times A dot B. So, P dot B is equal, we're going to need a new page. Let's create a new page. Try to do that in your paper notebook, y'all. Okay, so then P dot B, if we follow this previous, if we continue that previous line, recall that a determinant is just some number. It's just some scalar. So I could write out the formula for it, but I'm going to pause on that for just a second. And what is I again? Well, we use I in three-dimensional space to mean the unit vector in the first coordinate. So, P dot I. Oh wait, no. Sorry, oops. I dot B is 1, 0, 0 dot product with B1, B2, B3. And therefore, P dot B is B2, B3, B2... Oh, wait, no. B3, C3 is what I meant to write here, I think. Oh, no. No. Slow down, John. Slow down. This one was a typo, and I meant to say C2. This one should be C2, C3. Yeah. Now that's fixed. So, I dot B is the dot products of these two, which is just B1. Similarly, J dot B is going to be B2, and K dot B is going to be the third component. Okay, so now we have those mathematical facts, and I'm going to say, therefore, P dot B is the determinant of this minor matrix times B1 minus the determinant of this minor matrix times B2 plus the determinant of this last minor matrix, B1, B2, C1, C2 times B3. And we can now finally just calculate and expand these determinants, I should say. So this would be B2 C3 minus B3 C2 all times B1 minus, we're going to need three terms, so why don't we just do them right here. B1 C3 minus B3 C1 times B2 plus B1 C2 minus B2 C1 times B3. For anybody who is new and might be watching this out of curiosity, I used a fact that I didn't explain or justify. Right now, this is the determinant of a 2x2 matrix. So these symbols where I'm drawing two vertical bars and four numbers inside, what this is finding is the area of a parallelogram that is spanned by those two vectors. That's the intuition. That's where this idea comes from initially. And then we use it. We find a lot of other nice properties about it as well. But we calculate it, and I remember it as this forward diagonal AD minus this reverse diagonal minus BC. So you can use geometry to show that this is true. Geometry using this parallelogram, you can slice this up into right triangles here, and my parallelogram's really funny looking. You move that triangle over here, and then you have a rectangle, and you just do a bit of geometry, and you find that this is the formula for that area. Okay, so now, now we're gonna collect terms. So how do I want to organize these so that our lives become... Alright, I'm not going to try to be clever. Let's just frickin' do it. B1, B2, C3 minus B1, B3, C2 minus B1, B2, C3 plus B2, B3, C1, B2, B3, C1 plus B1, B3, C2 and minus B2, B3, C1, B2, B3, C1. Okay, so I'm pretty sure that I did all my distributions correctly there. But, you know, I make mistakes a lot. B1, B2, C3. B1, B2, C3 is positive and minus in those two terms, so they cancel out, right? B1, B3, C2. B1, B3, C2 is here, a negative value and a positive value. Those cancel out. And finally, the last one, B2, B3, C1, positive and negative. So this is equal to 0. Okay. Now... Oh, hey, Sensei. How's it going? Mod Hassan Ali. How are you? Dude, good to see you. Okay. Okay. Let's see. How's it going, dude? How are you? I'm going to try to cheat, sort of. The argument for P dot C is similar. it's the same thing. It's just that this is C1, C2, C3. And so I mean, this is kind of cool, I think, because I can use technology to duplicate and rewrite this very quickly. So the argument for P dot C is going to be essentially the exact same thing. These terms on the right would be C1, C2, C3 instead. Well, I mean, I guess let's take it all the way, dude. Let's go all the way. And let me rewrite all of this. Yoink. Okay, so we haven't yet shown these cancellations. Let's get rid of those. It's going to be pretty much exactly the same. Except in the first term, we distributed B1 here. Now we have C1, C2. Oh, wait, no. C1 and C1. In the second, or in the third and fourth terms, we distributed B2. This time we're distributing C2. And then in the last terms, we distributed B3. My alphabetization is all broken, but you know what? It's okay. It's okay. We could get even fancier, and if I were typing this up in LaTeX or something, then it would be a little bit nicer. But if you squint, B2, C1, C3. B2, C1, C3 is here and here. Positive and negative. I'm saying them out loud in order, in an alphabetical and a lexicographic, alphabetical and ascending numbers, so that I can spot which ones match. B3, C1, C2. B3, C1, C2 is here and here. And B1, C2, C3. B1, C2, C3, negative and positive. So all of this is equal to 0. And we are done. We are done with this proof. So I think this is a pretty cool problem, because it is more conceptual. We didn't work with concrete numbers this time. We showed that the cross product of two vectors, of any two vectors, B cross C is orthogonal to B, and B cross C is orthogonal to C. This is a cool little property that we just showed is always true. And it's cool that, to me, that the book did not prove this in the section. It left it as an exercise to solve. So that's heck yeah. This book is fairly conceptual, I think. More so than some other famous books that I've tried to read. Okay, so that was problem from section 1. Dude, how's your day going? Mode Hassan Ali, how are you? All right, we got somebody in chat. We got somebody in chat. Let's put chat up. How's it going, dude? How are you? I like that exercise. I think that was a worthwhile exercise. Now we're going to section 2. The determinant of a square matrix. Okay. So, we find in... You're fine. Good, dude. Happy to hear that. There are some special rules that we can memorize. There's a special rule for a 3x3 matrix. When we have... I'm just going to write little dots. The determinant of a 3x3 matrix. You can what you can do for a 3x3 matrix is duplicate the first and second columns. I'm going to write maybe like open circles or something to signify that those are like duplicated. They're like repeated, column 1 and column 3. I guess if I wanted to make it a little bit more clear, the determinant of column 1, column 2, column 3, you think of this matrix. I'm going to write this in brackets because I want to make clear that we're not taking a determinant of this new rectangular matrix. Instead, we're creating an augmented matrix where the fourth column is a copy of column 1, and the last column, the fifth column, is a copy of column 2. So that's why I drew like an arrow here. We copy column 1 and column 2 in those two. And then you multiply across the entries forward, and you get some complicated numbers, and then you subtract the reverse diagonals. So this is kind of it's a shortcut. It's a trick that works well for calculating a 3x3 determinant. But it doesn't work for larger matrices. So don't try to memorize this and think of this for 4x4 or 5x5. You have to remember that these tricks of like a 2x2, you can do this like for a 2x2, you can find that product and subtract the other product. And for a 3x3, you can do something similar, but you can't do that for 4x4 or 5x5, etc. So I'm going to work this problem two different ways. First, we're using our one weird trick. So let's put this in practice. Let me show you what I mean exactly. The determinant of this is going to equal, so I write the matrix again, 0, 1, 4, 2, 3, 1, 1, 4, 1, 0, 1, 2, 3, and 1, 4. So I copied the first and second columns. I'm going to multiply across the forward diagonals, and we get 0 plus 1 plus 32. Right? And then we're going to subtract 12 plus 0 plus 2. And this is 33 minus 14, which is 19, right? So the answer for this determinant should be 19 if I didn't make a mistake. It's pretty easy to make math mistakes a bunch of places. Did I mess it up? No, I think 32 minus 2 is 0. Oh wait, no. 32 minus 2 is 30. 30 minus 12 is 18. 18 plus 1 is 19. Yeah, so that's another path. So I didn't make a algebra mistake. All right, so that's one solution. Let's get another solution. This is the definition of an arbitrary sized matrix. Dude, I don't know if I can write down the precise definition, because it's kind of tricky to write it. I don't have it completely memorized, but it's like, we do an expansion along, I think usually we define it as an expansion along the first row. A11 times the minor matrix that you obtain by removing row 1 and column 1. So let Aij be the matrix after removing row I and column J. So I like slice out, I cut out the first row and first column, and then I subtract the second component, the second cofactor, which is A12 times the determinant of the minor matrix 1, 2. So we cut out the first row and second column for that one. And then we do plus and minus, dot, dot, dot. So the sign keeps changing. Plus, minus, until we get to -1. If n is even, then this last term is negative. So if n is even, like if it's a 2 by 2 matrix, this is an alternating sign, plus, minus. So then when n is even, the sign is negative. When n is odd, the sign is positive. Okay, So this is like the definition of the determinant in terms of cofactors. That's a complicated formula, and it's very complex to use. But it is the formal definition from which we can prove a lot of properties. In summation notation, we have from j equals 1 to n, we have an alternating sign, -1 to the j plus 1, or j minus 1, however you prefer to think of it, times a, the cofactor, or the coefficient 1j times the determinant of the minor matrix 1j. So this is the definition of a determinant. And it's difficult to work with directly, as I said. Hey JC, how you doing? I'm doing okay, man. I'm doing okay. I am cautiously optimistic about a couple of new job opportunities. I'm trying to become a math teacher, man. Like I'm trying to start teaching math someday, because I really like it, obviously. I'm here giving away free tutorials, like free lectures on linear algebra on YouTube. So if a matrix has a full row or column of zeros, the determinant is 0. Totally, that's absolutely true. And we can prove that right now, because this is the definition of the determinant. Well, almost. If from this definition of the determinant, if the first row is all zeros, then each of these would be 0, right? So that isn't quite enough. It isn't quite enough to say if any row or column is zeros. But from this definition, I can see that if the first row is zeros, then this factor, this coefficient is 0, and so then that term in the sum is 0. But if the first row is not 0, remember that this matrix cuts out that first row. And then, so this minor matrix slices out that first row, maybe in blue. When I slice out the first row and first column, we calculate the determinant of this smaller matrix. Well, at some point, we will reach that row of all zeros after doing this a few times. So eventually we'll get to the, maybe the row of all zeros is the fourth row or something. So after 4 times, calculating these minor matrices, eventually you'll get to one where the first row is all 0, and then this part of every term is 0, and then therefore everything is 0. So what I'm trying to get at is, like, yes, that is a true fact. That is a true statement, that if any column or row is all 0, then the determinant is 0. But why? You could prove it directly from the definition, like I just did. Now, there's more powerful tools. There are row and column interchange. You can prove a theorem that you can expand along a column instead of a row. You can prove a theorem that says that you can expand along any row or any column. But yeah, like right now, I just worked directly from the definition to prove the thing that you just pointed out. Since they joined universities like Harvard, I wish they wouldn't hire me. I don't have a master's degree. I don't have a PhD. Dude, I could never teach at Harvard, but cofactor expansion, multiply each first row entry by its signed minor and sum. Yeah. That's this definition right here that you're talking about, I think. Okay, so there's a little bit of theory. I calculated the determinant using our one weird trick for 3x3 determinants. Now, let's use cofactor expansion. And I feel like it's actually, in this case, going to be easier than the 3x3 special rule. So, following the fact that we just talked about, we have 0 times the minor matrix 3, 1, 4, 1. Like slicing out the first row and first column. 3, 1, 4, 1. Minus 1 times the determinant of 2, 1, 1, 1. 2, 1, 1, 1. Right? And then plus 4 times the determinant of 2, 3, 1, 4. 2, 3, 1, 4. Okay, the determinant is always just a number for any matrix. So 0 times a number is 0. And here I can calculate that this is using the 2x2 rule. That and 4 times 8 minus 3. So this is -1 plus 20. And this is 19. And we get to the same answer that we did earlier with the special... I did the special 3x3 rule to get 19 earlier. And now, from the definition, and the more general definition of a determinant, it's kind of like we live in 3D space. So I can talk about the volume of this iPad or something, you know, like I can talk about the volume of a box in 3D space. But like, let's just imagine we live in 10 dimensions and 11 dimensions. Let's imagine we live in 11 dimensions. How can we extend this thing that we found in our world into 11 dimensions? Well, this turns out to be the formula that works for higher dimensions. Cool. Okay, so we did that problem. And then to that point, now we are going to go to section 3. And here, this is a 5-dimensional determinant, 5th order determinant. We could absolutely use the definition, but that takes a lot of time. It's like really kind of tedious to do it that way. Instead, I'm going to utilize some properties of the determinant. Properties of the determinant. The determinant of A is equal to negative determinant of A prime, where A prime interchange to rows or columns. So if you swap 2 rows or columns, then the value of the determinant is the same, but multiplied by -1 with an alternate sign. So this determinant is equal to the negative determinant of, I want to swap the first and second rows, -1, 4, 1, 0, 0. I like working with 1 in my top left in like the pivot entries. It just makes your life easier, I think. 3, 2, 0, 0, 0. 0, 4, 1, -1, 2. It's kind of like Sudoku or something, you know? It's not the worst way to spend 5 minutes if you're really, really bored. -1, 3. Okay, now another property of the determinant. The determinant of A is equal to the determinant of A prime, where A prime adds a multiple of one row or column to another row / column. I mean, of course, you can't add a row to a column, but you can add rows to other rows, a multiple of any row to another row. So what does that mean? Let's be more precise about that. Let's keep the first row the same. Let's keep the third row the same. I think you see where I'm going with this. 0, 0, -3, 2, 4, 0, 0, 0, -1, 3. Now, our new row 2, I want to add row 2. So it's important that row 2 stays fixed. You can't multiply it by a negative or multiply it by a multiple of itself in this process. It needs to be row 2 so you can add a multiple of another row to the row in question. So we're replacing row 2 with row 2 plus 3 times row 1. So if I add 3 times row 1 to row 2, then we have 0, 12 plus 2 is 14, 3 plus 0, and then 0, 0. Right? Now, well, other properties of the determinant. We need to prove all of these things. The determinant of the matrix A, how do I put this? The determinant of the matrix can be calculated by cofactor expansion of columns instead of rows. And I think that's because, is it true that the determinant of A equals the determinant of A transpose? I am forgetting. Is that true? Yeah, that's what I thought. Uh-huh. So this is a corollary because determinant of A is equal to the determinant of A transpose. So A transpose, you write rows as columns and columns as rows. So what used to be the first column in the transpose matrix, it's the first row. And then you just use the definition. This is -1 times the determinant of this thing, and -1 times -1 on the outside scalar. Well, this is just the 4x4 determinant of 14, 3, 0, 0, 4, 1, negative 1, 2, 0, negative 3, 2, 4, 0, 0, negative 1, 3. How do I want to go from here? Well, it's a little tricky. I mean, determinants are like we could split this into two 3x3s, but it's just nice to look for more clever arguments when you can. Oh, I see. Oh, wait. Well, I was going to subtract row 3 from row 1, but that doesn't really help that much. It might simplify things, but let's introduce another property of the determinant. So if I multiply a row, essentially, like, you can factor out a scalar multiple of a row or a column. Aha. So this is nicer. So since we can factor a scalar multiple of any row or column, this is a little nicer if I factor out 2 from the first column. So this is 2 times the determinant of 7, 2, 0, 0, 3, 1, negative 3, 0, 0, 0, negative 1, 2, 2, 4, negative 1, 3. We need a new page. And let's start working horizontally as well as vertically. Oops. Shoot. Okay. Now, let's subtract 3 times a second from the first, just to work with 1 instead of 7. So 7 minus 6 is 1. 3 minus 3 is 0. 0 minus negative 3 is positive 3. 0 minus 6 is negative 6. Again, I replaced row 1 with row 1 minus 3 times row 2 here. And we're going to keep row 2 the same. Here, let's be more clever than that. Ha, my handwriting's getting out of sync, but whatever. Now, in row 2 prime, let's subtract 2 times row 1. So you see how I went back and forth between row 1 and row 2 to reduce a 7 to a 1, and now it's just much easier to work with. So 2 minus 2 is 0. 1 minus 0 is 1. Negative 1 minus 6 is negative 7. 2 plus 12 is 14. Then the rest is the same. Now, what's cool is that I have a column I have a cofactor expansion along this column. So here we can do 2 times 1, negative 7, 14, negative 3, 2, 4, 0, negative 1, 3, and 1, negative 7, 14, add 3 times the first row to the second, so negative 21 plus 2 is negative 19. 3 times 14 is 42. Yep, 42. Plus 4. 42 plus 4 is 46. And we have 0, negative 1, 3. I don't see any common factors to factor out, so we have 2 times negative 19, 46, negative 1, 3, the determinant of that. This is 2 times negative 19 times 3 plus 46. And this, negative 60 plus 3 is negative 57. Negative 57 plus 46 is negative 11. Negative 11 times 2 is negative 22. Woo! I wonder... Bye, Sensei. Hey, take care, Mode. Good to see you, bro. Good to see you. May your prayers be accepted. Thank you, dude. I'll be here if you want to dive back into linear algebra determinants when I return. Heck yeah. Thank you. Thank you, dude. Okay, so 4.3.6. It's very possible that I made a typo in the process of this. I don't really feel like... let's do it. Let's type it into a determinant calculator and just find out. Did I... Because it makes me feel good whenever I did not make any typos. Determinant, Wolfram alpha. Wolfram alpha. Okay, so we have curly brace, 3, 2, 0, 0, 0. This is going to take forever. Negative 1 for 1, 0, 0. And at this point, I literally have a lot of opportunity for typos. 0, 0, negative 3, 2, 4. 0, 0, 0, negative 1, positive 3. Did we get it? Boom! Negative 22. Look at that. I got it. Heck yeah. All right. So let's cross that one out. Keep moving. 4.2.5. I forgot to cross this out. Cross it out in my book, in pen. Never do that problem again. 4.3.6 is done as well. Finally, the last problem we have today is on linear transformations and determinants. This is an optional section. This is cool. Find the volume of a 4 box in R5. So this is a smaller dimensional thing in a larger dimensional space. We can think of that like in R2 in the plane, what is the area of a line segment? Like this is, the area is just length. In 3-dimensional space, maybe we want to find the area of two vectors, and then this determinant finds area. This is like a 2-dimensional subspace of three-dimensional space. Similarly, we look at the volume of a three-dimensional volume in R4, etc., etc. Well, the way we can find this, we have a very nice theorem that's the volume of an n box in Rm is the square root of the determinant of A transpose times A. Well, why would this be true? First off, A is a span of n vectors, and recall that n is less than m. We're finding an n box in Rm, right? Maybe I should be saying m less than n, but I don't know. We usually use n then m. Anyways, this is not a square matrix, right? It's not square, so determinant of A is not defined. It does not exist. So A is each of these VI is in m-dimensional space. Each of those vectors are m-dimensional, so A is an m by n, m rows and n columns, right? And A transpose, rows are interchanged with columns, right? So A transpose would be V1 written as a row up to Vn written as a row. And A transpose then is an n by m matrix. Therefore, A transpose times A is n by m times m by n. So A transpose A, I remember this by like this m and this, the number of columns of the first needs to match the number of rows of the second. But if I'm honest with you, I remember it as like this number, this second number needs to match the first number. And then we get an n by n. So this is an n by n matrix, also known as its square. Therefore, determinant of A transpose A exists. Because the determinant is only defined for square matrices. We might take notes later, but probably not. Maybe not. Maybe not. So the determinant of the transpose times A exists. Now, how can I prove that it would be equal to the volume. Like, why does A transpose times A match the volume of that box? I don't know exactly, but at least we got a little closer to understanding this theorem, and I might take notes on this section after this, but I know that this is the theorem that we use in this case. So, enough of that. Let's, oops. So, we'll name these V1, V2, V3, and V4. So our matrix A is, here, I'll go ahead and write both of them. And let's just go ahead and say determinant of A transpose A is the determinant of, what is A transpose? We write the vectors as rows instead of columns. 1, 1, 1, 0, 1. 0, 1, 1, 0, 0. 3, 0, 1, 0, 0. 1, negative 1, 0, 0, 1. And in our matrix A, we do the usual way that we represent a set of vectors as a matrix. We write them as columns. 1, 1, 1, 0, 1. 0, 1, 1, 0, 0. 3, 0, 1, 0, 0. 1, negative 1, 0, 0, 1. So we can, I don't really like this notation. I think it's technically incorrect. The determinant of the multiplication of these two matrices. So let's do this matrix calculation. These are going to be the dot product of each vector with, well, at least along the diagonal, it's a dot product of each vector with itself. Maybe not for everything. So this is going to be 4 in the top left entry. Then we have 2 in the second entry. Then we have 3, 4, 4 in the third. And then we have 0, 1. Yep. Then now we have 2 here. We have 2 here. We have 1 in this entry. We have negative 1 in this entry. We have 4 in this entry. We have 1 in this entry. We have 10 in this entry. Oops. And we have 3 in this entry. 0, we have 1 here. We have negative 1. We have 3. And the final entry, we have 2. We have 3. I'm starting to get nervous that I might have missed a double negative somewhere else. So I was like kind of ripping through these. No, I think that might be. Yeah, that's the only time that there's a double negative. Yeah. Okay, so Now, again, we do our row reductions. I'm going to interchange the last row and the first row. 4, 2, 4, 1. 1, negative 1, 3, 3. I'm going to subtract 2 times row 1 prime from row 2. So 2 minus 2 is 0. 2 plus 2 is 4. 1 minus 6 is negative 5. Negative 1 minus 6 is negative 7. And then row 3, I'll subtract, either you could think of it as row 1 or row 4 prime, either way. 4 minus 4 is 0. 1 minus 2 is negative 1. 10 minus 4 is 6. 3 minus 1 is 2. Okay. And while we're at it, just in place, let's update this last row. Let's make sure we don't make a mistake there. 4 minus 4 times the first row is 4. 2 plus 4 is 6. 4... Yeah, 4 minus 12 is negative 8. And 1 minus 12 is negative 11. Okay. Wait, what the heck did I... Oh, 4... Whoops, I forgot the point. Right here. 4 minus 4 should have been 0 right there. Yeah. Okay. So this is the negative determinant of the 3 by 3 matrix. 4, negative 5, negative 7, negative 1, 6, 2, 6, negative 8, negative 11. Okay. I'm going to add the second column to the first. Yeah, add the second column to the first. 6 plus negative 1 is 5. 6 plus negative 8 is negative 2. Then let's add 5 times, no, let's subtract 5 times the first column from the second column. So negative 5 plus 5 is 0. 6 minus 25 is negative 19. Negative 8 plus 10 is 2. Let's subtract the second column from the third column of the prior matrix. Then we have negative 2. 2 minus 6 is negative 4. Negative 11 minus negative 8. Negative 11 plus 8 is negative 3. Okay, we're getting somewhere. Factor out a negative 1 we'll factor out a negative 1 from the first row. And subtract 2 times the first column from the third column. So 2 minus 2 is 0. Negative 4 minus 10 is negative 14. Negative 3 plus 4 is 1. So let's work in this direction. Well, this is going to be the 2 by 2 determinant if we expand so we're working this direction. If we expand by the first row, then we have the 2 by 2 determinant, negative 19, negative 14, 2, 1. And this would be negative 19 plus 56. 14 times... Wait, no. Wait, why did I double twice? Yeah, negative 19 plus 28. And this... I'm confusing myself for a second here, is 9. I think that... Yeah, I think that's the answer on this one. Is it an odd problem? Or an even problem? It's an even problem. What we could do is punch this thing into the matrix calculator, or ask ChatGPT. If we want to burn a lot of water, so if I set up the problem correctly, then the value of this determinant, 2, 2, 1, negative 1, 4, 1, 10, 3, and 1, negative 1, 3, 3. Nine. Look at that. I got it. Getting good at these determinant calculations. No typos today. Awesome. Well, we worked a problem from every section. Do I feel like taking notes today? Maybe. Nobody's here at the moment. So I kind of feel like I'm sort of wasting my time a little bit. But, you know what? I like math. I like math a lot, so why don't I just spend my time studying math? Anybody here? Anybody lurking? No, not at the moment. Alright, that's fine. Okay, alright. So, let's take some notes. Let's just chill and take some notes, y'all. Here's my guitar recital that I'm very proud of. I hope y'all check it out sometime. That's me. So, yeah, I feel like every practice session should have some theory, like actually taking real notes, reading the sections, not just doing calculations every time. You know, it's important to work through the theory as well, even if I'm just reviewing it for myself. It's important to write this stuff down. So today I want to take notes on the section that we just worked, section 4. That's me. I hope you enjoy my music. Let's turn up the music. I'm going to practice privately for a little bit. Y'all, what's going on? I doubt anybody's still watching this, but if anybody is watching this, I hope you enjoy, y'all. Thank you for watching. Thank you for hanging out with me. Thanks. Oh, I intended to turn up the volume of this video. Whoops. I keep messing this up. Cool. All right. I doubt anybody's ever going to watch this part of the video. If you are, thank you. Thank you for hanging out with me. Thank you for watching. You must be a fellow math nerd like me. I just took some notes on this section. I think I learned a lot just now. Yeah, pretty freaking cool. Yeah, I have a better appreciation for how these determinants can be connected to integral calculus, especially with regards to change of variable, like variable substitution. So thanks y'all. Thanks for watching. I'm gonna go ahead and sign off. Thanks for watching. Bye.